electrons to get out of the anode and into the cathode.
So like it would be Cu in the Fe solution?
Yes.
So you put
Yes.
the Cu bar into the Fe solution?
Nope. You need to separate those two reactants from one another, because if you just put a copper bar into an Fe solution, they might directly react with each other. You need to have two different compartments in one of these cells and a wire going across them. That wire is carrying current. That current is what we use to run our electrical things.
So we put a copper bar into the copper solution?
Yes, that's right. That's right. Yep. And we'll see all that in just a second. But let me just show you a little bit more about line notation. Be aware that if the electrode has to be some interconductor like platinum, then you're going to put it either right here if it's in the anode or right here if it's in the cathode. Sometimes you need platinum both here and here. If you have all aqueous things reacting in both compartments, then you're going to have both platinum electrodes. And that's fine. So those single lines are separating the electrode from whatever solutions are in the compartment. Here's another example of line notation. The zinc-hydrogen reaction. We had done this one yesterday. You got a bar of zinc reacting with hydrogen ions, and that makes zinc ions and H2. The H2 is bubbling up. Remember at the end of that graphite, the platinum rod, how the stream of bubbles was coming out of it yesterday? Right back there behind Nick? Yeah. That was the production of hydrogen because hydrogen ions were reducing to hydrogen gas. Now, the anode has zinc metal changing to zinc ions. So that would have a zinc bar in it. I had a zinc bar yesterday that I was using in that part. Over on the other side, that's where I had to use the graphite bar, or the graphite rod, because I needed to use an inert electrode. Hydrogen ions were changing to hydrogen gas. So the line notation for this reaction is going to look like this. Over in the anode, it's very simple. Zinc metal changes to zinc ions. We're done. In the cathode, though, the hydrogen ions are accepting the electrons to make hydrogen gas. Both of those go together. I just put a comma in between the two. Now with normal chemical equations, we put H plus yields H2. But with line notation, you're right, H plus is what you start with, comma, H2 is what you end with. Lena?
So how come the electrodes are outside?
That's the way line notation is written. The implication is that the wire is going from this end to that end. And so, yeah, that's the convention that's used. Go ahead.
I see. So when we're using electrodes, why wouldn't we put like a bar? So we would put a bar of Cu, and then like how would the chemistry work? Because wouldn't they both be gaining ions?
No. I'll show you what happens. And thanks for asking that, too, because it's not intuitive at all until you kind of get the hang of what's going on. So we have two. I'm going back up to this equation. That's what you're talking about, right? Up here with iron and copper. So here's my anode, where the iron is reacting, and here's going to be the cathode, where the copper is reacting. I've got a bar of iron, and then there's a bar of copper over here. There's a wire attaching them. Yeah? Salt bridge always has to be there. I'll use a different color for the salt bridge. My nice YouTube. On paper, it's great. It's just in reality, it's difficult. Okay. Now, in this solution, there's going to be Fe plus 2. In this solution, there's going to be Cu plus 2. The iron oxidizes. We see that from the chemical equation. Fe is changing to Fe plus 2, so we have an oxidation of the iron. So this iron is going to be losing electrons. That's oxidation at the anode. So the electrons leave the iron, and they go that way. What happens to this bar of iron? It gets smaller because as the atoms of iron lose their electrons, they cannot hang on to the bar. That bar has to be neutral iron. So as soon as they lose their electrons, they drift off into the solution. So what's happening to the concentration of this Fe+2? It's going up. Yep. The whole time that current is flowing, we're getting more and more Fe+2. Over here, these electrons are coming in. Now the copper bar doesn't want electrons. It doesn't have any. That would make it negative copper. When have you ever seen negative copper? No. How about this copper? Does that like a couple of electrons? Yeah. So what happens is these ions join up. When they sense that the electrons are coming in here, they're over there immediately, and they can grab on, and they'll make more neutral metallic copper. What happens to the size of that electrode? It gets bigger. Yeah. Now, in reality, we would not see it getting bigger because you'd have to run this thing for a long time to visually see it getting bigger. It would just plate on a new layer of copper. You might take it out and notice, oh yeah, I can kind of see where it plated. But you can't really tell if it's swelling up like that. It does get bigger though. If you measured it, it would be heavy. So is that a better picture of what's going on? As the electrons flow, this increase in concentration, this is going to decrease. Before, I mean, at the end of this reaction, there will be no copper ions left in the solution. All of them will have grabbed on and become part of the copper bar. And at that point, the reaction's over. There will be no more voltage because this concentration is so low. There's nothing else to accept the electron. Does that make sense? All right. Good. The next thing I'm going to ask you to do is you draw a cell. Let's take a look. This is an example in the book. Sketch the galvanic cell based on the overall reaction. Here's our overall reaction. This is another simple one, like the iron copper. Show the direction of electron flow, as I have done over there. Show the direction of ion migration through the salt bridge. So I didn't do that over there. Identify that cathode and anode. Give the overall balanced equation. Is this equation right here balanced? Huh? Hardly balanced, you're right. 1, 1, 1, 1. That's not balanced?
The electrons are balanced.
The charge is not balanced, that's right. What do we have to do to balance it?
And electrons
2 AGs, 2 AGs. That'll take care of it. Yeah? Now, if it weren't so simple, you'd have to break it up into half reactions and do that whole half reaction business. I like that. Yes?
Does that mean you have to like draw it twice about the like silver ions and whatnot, or there are two different
You don't have to in your sketch.
Okay.
You don't have to.
So like on lab reports, we do particular drawings.
I'd expect you to write the balanced equation for it, but on your particle model, I want more than one of everything like I always do. But no, you don't have to write twice as many silvers in the one compartment as irons in the other. That's fine. Sir?
They didn't identify the salt in the bridge.
They didn't identify the salt bridge?
The salt in the bridge.
It doesn't matter. Just use negatives and positives for the migration of ion flow. Okay? So I want you to just try this. Even if you're frustrated with it, just work with a person around you, if there's a nice person around you, and try to figure out how to answer all this. And by the way, I'm going to tell you right now, today's Friday, you've got a quiz in 10 days. On that quiz, I will ask you a question just like this. I'll probably have a different chemical equation, but one of the 5 questions is going to be, sketch the following cell, label the direction of electron flow, label the anode, all that. This is for sure going to be on the quiz.
Will you make us do the half reaction for that?
I don't make you do anything.
Well, will they read a question that involves the half reaction method?
Good idea.
No,
Okay.
not a job.
I didn't think of that before. But yeah, that would be more work to do.
Good job. That would take more time.
Yeah, you got lots of time.
No,
No,
you
we
don't.
don't.
It's no big deal.
Good job, Parker.
That is a really good idea.
Now everyone hates you. Why? How would you do that?
Sarabi.
I'm lovable. What have you done to me?
Okay, try that. Talk to each other, please.
So I can't. Are you reading your book?
Do we have to write it in line notation?
This one doesn't ask for line notation. The next one will.
Even your
What time was it
phone.
gonna be when class at 12:40, right?
Yeah.
And are we 12:40?
12:30.
It's only 12:30. Oh, 12:42. 12:42.
Now, you're doing that now. Writing on a white piece of paper.
Oh, I just grabbed the numerous people that I had and
I'm a trendsetter, guys.
Or wait, no.
Aren't I?
I didn't say I'm.
Don't you forget that salt bridge either when you
Let's get taken trees off.
Sophie, you won't have any currents if you don't include the salt bridge. Yes, yes you will.
The
salty.
Do you know Leslie?
Salty bridge.
Leslie?
Oh,
She's reading this on her own. I have to read this down. She's like, I'm reading this down. And I was like, yeah, I brought it. It's in my bag. She's like, it's in my bag. I was like, yeah. She's like, yeah, I brought it too.
I got the 155.
If you start at the center. Wait, Mike, you get off then you go around in a circle. Okay, around the table,
And the middle part is where all installed.
I started this thing, I haven't labeled anything, which is really, everybody's sketches will always start like this. Anybody interested in going and filling that in?
Oh, yeah.
Vinny, that's cheating. Nick, you want to try this? Okay.
What? How is it?
We should just make this more serious.
I think that's, yeah. Yeah, I think that's right. How do you,
You don't have to. Have we missed anything?
is that the iron?
Oh, it says give the overall equation, but I've already talked about that. Identify cathode and anode. So make sure when you get these questions, make sure you check off everything that it asks you to do. Because look, how many things does it ask you to do in that paragraph? Same thing on the quiz. Don't miss anything.
What's the iron migration?
Yeah, what's that? No, don't worry about that part. Good job, Nick. Now, here is my edition of it. And how did Nick do?
Great.
Now, direction of ion migration, what I've done, Nick had a perfect answer. This is absolutely perfect. A lot of times I'll just put like negatives kind of migrating down this way, positives migrating down this way. That always is going to go in that order. The negative ions always have to go into the anode. Because the anode is losing negative charge, the negative ions have to be there to replace it. And the same thing goes here. Negatives come in here, so we're building up negative charge. We need the positives to come in here and neutralize.
How do you even do that?
Do what?
On that. Like,
I have, on that notebook program, it will have beakers like as clip art, so I didn't have to draw the beakers. This I
like,
just
that'd be a perfect
shaded in
figure.
some rectangles for that.
Wow.
So, if you like draw negatives coming from the cathode and like positives coming from the anode, will that still be fine?
Negatives coming from the cathode.
Yeah.
How would you draw those?
Just like a negative sign, the arrow going on.
Negative sign, like in the beaker?
No, like in the salt.
In the salt bridge, negative way over here, with an arrow that's going like that.
Yeah.
What's over here?
Positives with an arrow going that way.
Oh, just because you're showing, I see what you're saying. It's like the negatives may be over here, but they're tending to go that way. That's cool. That's cool. If your arrow's in the right direction, I'm happy. I understand what you're saying. Okay, anything else about this? Now, I was hoping that we would have enough time to try one more example with line notation. This one is going to ask you, yes, another picture, sketch the cell for this reaction. Oh boy. This looks like fun. you gotta add the oxygen.
Substitute.
Well, you gotta